Very good day to Dr. Safiano. We are from Group 2E Section 2. Our presentation will be focusing on smart dustbin with garbage monitoring level.
Our group member consists Shaza, FARESHA, IMAN, SHERINA and LIYANA.
Assalamualaikum and hello everyone. I am NURUL HAIQAL ROSZAINI, AD23067. I would like to briefly discuss the background and motivation behind this study. Nowadays, waste disposal has become one of the major environmental challenges due to rapid urbanization and population growth. As the amount of municipal solid waste continues to increase every year, conventional waste management systems are becoming less efficient. Traditional waste bins still require manual inspection to determine whether they are full. This often leads to inefficient waste collection schedules, overflowing bins, unpleasant odors, and unhygienic surroundings. According to Ma'aluf 2022, global municipal solid waste is expected to increase to between 2.89 and 4.54 billion tons by the year 2050, representing a significant increase compared to 2019. Besides affecting operational efficiency, overflowing dustbin can also become breeding grounds for bacteria, viruses, flies, mosquitoes, and other insects. This condition may increase health risks and reduce the cleanliness of public area. In addition, users are required to manually open the dustbin lid, which increase the possibility of contact with germs and contaminated surfaces. To overcome this issue, recent development in automation and sensor technology have introduced the concept of smart waste management system. Our project proposed an automated smart dustbin that is capable of monitoring the waste level in real time. The system uses an ultrasonic sensor to measure the amount of waste inside the bin, while a PIR sensor automatically opens the lid whenever a user is detected. The waste level is displayed on a LCD screen, and when the dustbin reaches 80% capacity or above, the system activates a buzzer to notify users that the bin should be emptied. Through this automated approach, the proposed system aims to improve hygiene, increase waste management efficiency, and create a cleaner and more sustainable environment. For this section, I will explain the aim and objective of our project. The primary aim of this project actually is to design and develop an automatic smart dustbin with real-time volume telemetry and threshold-based acoustic feedback. The purpose of this system is to improve waste management by making the dustbin more hygienic, efficient, and intelligent through the use of automation and sensor technology. To achieve this aim, we have established 5 main objectives, but I take 3 objectives to explain it. So the first objective is to develop an automated dustbin that can open and close its lid automatically using a passive infrared or PIR sensor. This allows users to dispose of waste without touching the lid, reducing the spread of germs and improving hygiene. So next, the second objective is to monitor the waste level inside the dustbin in real time using an ultrasonic sensor. Ultrasonic sensor is the sensor measures the distance to the waste surface and calculates the percentage of the dustbin that has been filled. So, final objective is to validate and evaluate the performance of the proposed system through simulation using Tinkercad and MATLAB, ensuring the system functions as expected before implementation. Next, I will explain the literature review, starting with the smart waste management system. Nowadays, the amount of waste produced is increasing rapidly due to urbanization and population growth. As a result, traditional waste collection methods are becoming less efficient because they usually follow fixed collection schedule instead of the actual waste level inside the bins. According to previous studies, smart waste management system overcome this problem by integrating sensor, automation, and communication technologies to monitor the waste level in real time. This allows waste collection authorities to optimize collection flows, reduce transportation costs, prevent overflowing bins, and improve overall operation efficiency. Therefore, this concept serves as the foundation of our project because our automated smart dustbin is designed to provide real-time monitoring and improve the efficiency of waste management while supporting sustainable smart city development. So the next component we should discuss in the literature review is the passive infrared or PIR sensor. A PIR sensor is commonly used for motion detection because it detects change in infrared radiation emitted by the human body or other warm object. It is widely used in automation system due to its low power consumption, low cost, and reliable performance. In our project, the PIR sensor is responsible for detecting the presence of a user approaching the dustbin. Once motion is detected, the sensor sends a signal to the controller, which automatically opens the lid. After the user moves away, the lid closes automatically. This hands-free operation helps improve hygiene by reducing direct contact with the dustbin, making the system more convenient and user-friendly. Next component in our literature review is ultrasonic sensor for waste level monitoring. An ultrasonic sensor is widely used for measuring the waste level because it performs non-contact distance measurement. The sensor works by transmitting ultrasonic sound wave and measuring the time taken for the reflect wave to return from the waste surface. Based on this measured distance, the system calculates the percentage of the dustbin that has been filled. Compared to contact-based sensor, ultrasonic sensors are more hygienic, reliable, and require less maintenance because they do not come into direct contact with the waste. Previous studies have also shown that ultrasonic sensors provide accurate and cost-effective solution for real-time waste monitoring, making them highly suitable for smart dustbin application. So the final section of the literature review focused on Tinkercad and MATLAB simulation. Before developing a physical prototype, simulation is essential to verify the system functions correctly. In this project, Tinkercad is used to design the electronic circuit, write the Arduino program, and simulate the operation of all components such as the PIR sensor, ultrasonic sensor, LCD display, servo motor, and buzzer. Meanwhile, MATLAB is used to analyze and validate the system performance based on the simulation results. Using these software tools allow us to identify possible errors at an early stage, reduce development costs, and improve the reliability of the final system before hardware implementation. Now that we have discussed the theoretical background and previous study related to our project, I will move on the next chapter. Thank you.
Hi, my name is SHERINA BINTI ABDUL and my matrix number is CD240049. What is PID? PID stands for Proportional, Integral and Derivative Control. It is a control algorithm used to maintain a desired output by continuously calculating the error between the set point and the actual value. Proportional control KP equal to 15. First, the proportional component responds directly to the current error. This means when the error is large, the control action becomes stronger. So, in my system, if the lead is far from the desired position, the servo motor will move faster to correct it. However, if the proportional gain is too high, it may cause slight overshoot. And that integral control, Ki equal to 2. Next, the integral component focuses on past error by accumulating them over time. This helps eliminate steady-state error. In simple terms, it ensures that the lead reaches exactly the desired position and does not stop short. But if the integral value is too large, it can cause oscillations. Derivative control, Kd equal to 1. Finally, the derivative component predicts future error by looking at the rate of change. It slows down the system as it approaches the target and reduces overshoot. This result is smoother and more stable motion of the lead. And then, what we get from overall, the PID controller improved the system by making it faster, more accurate, and more stable. The MATLAB code used to automatically generate the simulating block diagram for the system. First, the model created and opened using the new system and open system command. This initialized a blank simulating workspace. And then adding block. Next, the required block such as set input, sum block, PID controller, transfer function, and scope are added using add block command. Each block in the code directly corresponds to a component in the simulating block diagram. The set parameter function is used to define the position of each block. This ensures the diagram is well organized and match the desired layout. Okay, and then the blocks are then connected using the add line command. This defines the signal flow from the input through the controller to the output. And creating the feedback path is created by connecting the output of system back to the sub-mentioned log. This forms a closed-loop control system. Finally, the system is automatically arranged and saved. The complete simulating model is generated without manual drawing the diagram. This approach improves efficiency, reduces human error, and ensures a consistent system design. Then, the simulating block diagram of the closed-loop PID control system used in this project. The system begins with the step input, which represents the desired lead position and acts as the reference signal. This reference is then compared with the feedback signal at the summation block, where the error is calculated as the difference between the desired and actual position. The error signal is sent to the PID controller, which processes it using proportional, integral, and derivative actions to generate an appropriate control signal. This control signal is applied to the servo motor plan, which represents the physical system responsible for opening and closing the lead. The output of the plan, which is the actual lead position in the past, through the sensor dynamics blocks that models the measurement process. This feedback is returned to the sub-mentioned block, completing the closed loop system and allowing continuous correction of any error. Finally, the scope display the system response over time, enabling analysis of performance such as overshoot, settling time, and stability. Overall, this block diagram demonstrates how feedback control ensures accurate and stable operation of the dustbin lead.
Hi, my name is NURSYAZA binti SUHAIHISAM. My matric number is AD230060. So I will continue on the PID method. After we get the block diagram according to the coding we have shown just now, we will obtain the graph time response. So looking at the graph, the system achieves a very short rise time of just 0.24 seconds, demonstrating an exceptionally fast response to the input signal. So because the system is underdamped, it experienced an initial peak overshoots of 26.85% at the 0.52 second mark. So followed by the controlled transients, oscillations, and a minor undershoot. However, the controller stabilized the system rapidly, achieving a short settling time of 8.22 seconds. Most importantly, our steady-state error drops approximately to 0, meaning the final output matches our desired reference value exactly. Hence, these results prove that our PID configuration successfully delivers a fast, stable, and highly accurate system response.
My name is NURUL FARESHA and my matrix number is AD230026. Moving on, I will now proceed with the apparatus section of this project. The smart dustbin with garbage level monitoring system operates through the integration of several hardware components, each performing specific functions to ensure efficient and automated waste management. The Arduino Uno R3 serves as the main controller, processing sensor inputs, making decisions, and controlling all output devices. An HCSR04 ultrasonic sensor continuously measures the distance between the sensor and the garbage surface to monitor the waste level inside the bin. Meanwhile, a passive infrared or PIR sensor detects human presence and triggers the touchless operation of the dustbin. For user feedback, a 16:2 LCD display provides real-time information such as the garbage level and system status. A piezoelectric buzzer generates audible alerts when the dustbin is approaching full capacity. The automatic automatic opening and closing mechanism is performed by a microservomotor which acts as the system actuator. In addition, a 250 kilo ohm potentiometer is used to adjust the LCD contrast for better display visibility, while a 330 ohm resistor protects the LCD circuit by limiting excessive current. This is the detailed circuit view illustrating the wiring configuration and interfacing connections among the Arduino Uno R3, sensors, display module, buzzer, and supporting components. The system components are interfaced with the Arduino Uno R3 through specific pin configurations to ensure proper communication and operation. The HC-SR04 ultrasonic sensor is powered using the 5V and ground pins, while its trigger and echo pins are connected to digital pins 5 and 4 respectively for distance measurement. The PIR motion sensor is connected to digital pin 2 to detect user presence and initiate touchless operation. The microservomotor receives its PWM control signal from digital pin 3, enabling automatic lead movement. Meanwhile, the active piezo buzzer is connected to digital pin 6 to generate audible warning signals when the dustbin approaches full capacity. For the 16x2 LCD display, the register select pin is connected to analog pin A0, the enable pin to A1, and the data lines are connected to analog pins A2 and A3, allowing the display to present real-time information such as garbage level and system status. Additionally, a 330 ohm resistor is incorporated into the LCD circuit with one terminal connected to the positive 5V rail and the other connected to pin 15 of the LCD. This resistor limits the current supplied to the LCD. The dustbin system is controlled through software developed using the Arduino IDE, which integrates data acquisition, processing, and output control for automated and touchless operation. It starts with sensor data collection, where the HC-SR04 ultrasonic sensor continuously measures the distance to the waste surface to determine the field level, while the PIR sensor detects nearby human presence. Both signals are sent to the Arduino Uno for processing. The Arduino evaluates the inputs based on 3 conditions: normal state when the pin is below threshold, warning state when the waste level reaches 80% or more, and interaction state when a user is detected for automatic lead operation. Based on these conditions, the system produces outputs in real time. The LCD displays the current waste level percentage, the buzzer activates as an alert when the bin is 80% full or above, and the servomotor opens and closes the lid automatically when motion is detected, ensuring hygienic and convenient use. Overall, the software architecture enables smooth communication between sensors, controller, and actuators, ensuring reliable and efficient operation of the smart dustbin. To evaluate the performance of the smart dustbin with garbage level monitoring system, several simulation studies were conducted using Tinkercad and MATLAB. The experimental methodology focused on garbage level monitoring, automatic lead operation, and PID-based response analysis. The first assessment focused on the garbage level monitoring capability of the system. Different waste accumulation conditions were simulated to represent various filling levels from empty to nearly full. The HC-SR04 ultrasonic sensor measured the distance between the sensor and the waste surface, and the Arduino converted the measured distance into garbage level percentage. These values were displayed on the LCD in real time. In addition, the warning mechanism was evaluated by verifying the activation of the buzzer when the garbage level reached the predefined threshold of 80%. The second assessment evaluated the performance of the automatic lead mechanism. User presence was simulated within the detection range of the PIR sensor. Once motion was detected, the Arduino transmitted a control signal to the servomotor, causing the lid to open automatically. The lid returned to its closed position when no motion was detected. Multiple simulation trials were conducted to evaluate detection reliability, servo response consistency, lid stability, and overall touchless operation performance. To further evaluate the dynamic behavior of the lid control system, PID analysis was performed using the MATLAB. The investigation examined the effects of proportional, integral, and derivative gains on the lid response. Performance indicators such as rise time, settling time, overshoot, and steady-state error were analyzed to assess system stability and positioning accuracy.
Good morning, good afternoon, good evening, everyone. My name is BINTI, and my matrix number is CD240205. For this section, I will present the results of the garbage level monitoring system. The graph shows the relation between the measured distance and the garbage level percentage. The ultrasonic sensor was used to detect the distance between the sensor and the garbage surface. Based on the graph, when the distance decreased, the garbage level percentage increased. For example, at a distance of 80 centimeters, the garbage level was approximately 0%, indicating an empty dustbin. When the distance decreased to around 20 centimeters, the garbage level increased to approximately 80%. The LCD display was able to show the garbage level in real time throughout the simulation. This result shows that the ultrasonic sensor successfully monitored the waste level and provided accurate information about the dustbin capacity. This slide shows the performance of the warning system and automatic lid operation. The buzzer was programmed to activate the garbage level at reach 80%. This served as an early warning to inform users that the dustbin is approaching full capacity. This figure shows the Tinkercad simulation during operation. The blue object inside the PIR detection area represents a user being detected by the PIR sensor. Once motion was detected, the PIR sensor sent a signal to Arduino controller, which then activated the servomotor. As a result, the LID opened automatically without requiring physical contact. At the same time, the LCD continued displaying the current garbage level. This demonstrates that the sensing, monitoring, and control function were successfully integrated into single automated system. This slide presents the PID controller analysis carried out using MATLAB simulation. The controller parameters used were Kp equal to 15, Ki equal to 2, and Kd equal to 1. Based on the simulation results, the system achieved a rise time of 0.24 seconds, which indicates a fast response. The setting time was 8.22 seconds, and the overshoot record was 26.85%. In addition, the steady-state error was 0, meaning that the system was able to reach the desired output accurately. The proportional gain, or Kp, helped the system respond more quickly. The integral gain, Ki, eliminated the steady-state error, while the derivative gain, Kd, improved the stability of the response. Overall, the selected PID gains provided satisfactory performance, and the objective of analyzing the PID controller behavior was successfully achieved.
Now let's move on to watch our simulation video. The simulation begins by running the Arduino program developed for the smart dustbin with garbage level monitoring system. The program controls all sensing, processing, and output functions. When motion is detected by the BIR sensor, a signal is sent to the Arduino Uno. The servo motor then rotates to automatically open the dustbin lid for touchless operation. Next, the ultrasonic sensor measures the distance between the sensor and the waste surface. The measured value is converted into a garbage level percentage and displayed on the LCD.
When the garbage level reaches or exceeds 80%, the buzzer is activated to provide an audible warning that dustbin is approaching full capacity. Finally, when the measured distance falls outside the predefined operating range, the system rejects the reading and no garbage level percentage display.
Conclude, this project solution successfully developed an automated smart dustbin with touchless operation and real-time monitoring. The system can detect waste levels from 0% to 100% using an ultrasonic sensor and display the information on LCD. Besides, a buzzer alert is also activated when the bin reaches 80% capacity to prevent any overflow of the rubbish. Next, the control system performance shows that with the lid opening automatically from 0 to 90 degrees using a PIR sensor. By using a PID tuning with a KP15, Ki2, and KD1, the system achieved a fast rise time of 0.24 seconds and also a zero steady-state error, that ensuring the stable and accurate operations of the smart dustbin. Lastly, for a future improvement, we can use an IoT monitoring, cloud storage, mobile notification, and smart waste segregation on the future work. Overall, this project demonstrates the potential of automation and control system in creating a smarter and more efficient waste management solutions.